what's happening. Let's get right to it. So this is for the CFA, Newton's law. And based on the graph, how would you describe the net forces acting on a moving object? So this is the moving object. This straight line represents the moving object. Let me see if I get my design, my draw tools right here. All right. So the moving object is going in the flat line, no outside forces. This is a acceleration graph, so it's velocity divided by time. So whenever we have velocity divided by time, pick this right pen. I guess this would be cool. So we have velocity, which is meters divided by second, meters per second over second. So we're dividing again. So it's meters per second, meters per second. So anytime we have this type of quantities, we have to simplify this fraction. We're dividing the fraction. So it's m over s divided by s. So anytime you divide fractions, you're going to multiply by its inverse. That's going to give us over here m divided by s multiply by the inverse. What's s over 1 is 1 over s. We don't see the 1. That 1's kind of hidden there, but it's the numerator. All right. So m times 1 equals m, and s times s equals not 2s, but s squared. So meters per second squared, or position per time squared, we call that acceleration with the a. Okay, that's what a equals that. All right, that's one of the formulas for a. I'm gonna erase all that. Hope you got that. Okay, so this object is not accelerating. So it's not accelerating. So it's definitely not, increasing in acceleration over time. It doesn't have negative acceleration starting at high speed and dropping down. That's not occurring. Now, I beg to differ. So we don't have any of that stuff going on. It's a straight, nice little clean straight line. So the forces have to be balanced. The object in motion stays in motion, or object at rest stays at rest unless acted upon by an unbalanced force. So the correct answer, what I would want you to just type in this stuff in here. You got these draw tools, if I may. All right, the answer that you would need to put on here would be net force would equal 0. I'll make sure I get that highlighted for you. That net force will equal 0. Make sure you get that down. Net force equals 0 on this object. Let's try the next one. Newton's second law states that the force on a drag racer tire equals the mass of the car times acceleration. All right, for most, one of the most important factors determining a car acceleration is the tires on the car. This is because the force accelerating the car forward is provided by, and what does that provide? If you're walking on ice, and you don't have any traction up under your feet, you can slip. So the traction, we call it traction, that's friction. So you can slip if you don't have anything. You're not going to go anywhere. If the roads are icy and slick, your car's not going to go forward. You got to have a force to counteract your force to help to propel you forward. So that force is friction. You want to go forward, you need a little bit of friction. That's why cars with these drag racers and these tires that they have, those tires are like kind of sticky. They're called sticky tires. Just Google that, drag racing tires. You need something that can stay hugging the ground very well. So you need friction to prepare you forward. It may sound counterintuitive, but when you're walking, you're pushing back, and the friction is helping you go forward. Okay, so let's look at the next one. We got 10-kilogram mass resting on the table. I'm getting my little drawing tools out again. So I got this weight resting on a nice old table. That weight is 10. I don't like that color. It's tough. 10 kg. It's even worse. All right. That's the mass of the object. Okay. Now, the acceleration will be generated when a force of 20 newtons is applied. So force, let's say, is going this way. So the force applied is 20 newtons. And the counterforce, which is the friction on the table, the counterforce, slowing it down, is going to be 15 newtons. So the difference is a difference in forces. So the difference of those forces uh, is 5. Okay. So I have a difference of 5 for my force. Net force, NET, 5 net force. Force equals 5 net force. I'm all over the place. Now, I try to find what's called the acceleration from the formulas that you've learned in class. I give you a couple of them right now. We won't derive them, but I'll write it out for you. Acceleration can equal force divided by an object's mass. I have a net force of 5. Object mass is 10. And if I have a calculator, 10 can go into 5. Yes, it can. 10 will go into 5. Half as much, 0.5. 0.5. And we're talking about these forces, acceleration, so it's meters per second squared. All right. So force equals mass times acceleration. Let me get a different color. Let me break it down over here a little bit. All right. Since force or Newton equals mass, which is kilogram, times acceleration, that means meters per second squared. And I can divide that by the mass again, kilogram. It's going to cancel out. So I'm left with acceleration as my unit for this problem, okay? All right. If y'all needed to see that again, just play this video and pause that part. I don't have my best tools moving forward. My classroom got these automatic lights. There we go, it's a little better. All right, so I'm scroll down a little bit, excuse me. All right, this is a little tough little problem, right? So right here I have this graph. So the graph shows the velocity time graph of an object. What is the acceleration of the object from 6.0 to 10.0 seconds? So I got to find some changes here. So I need to find the acceleration. Acceleration, we're not going to use the force divided by mass formula for acceleration. We're going to use the good old changing distance and time. All right. So we can have acceleration equals delta, which means change in velocity, divided by delta, which is change in time. I can write that a different way. Acceleration equals the final velocity of object minus, so F, minus the initial velocity of an object. Divide that by the final time recording of our measurement from the initial time recording of our measurement. And I'll plug in the values that I'm given. So I'm going from here to here. So this would be my initial, starting here to here. So I'll work it out over here. So I have from here to here. Work out like backwards. So it's 6.0 is my initial. My 10.0 is my final. And I have to find my corresponding velocities for these time intervals. So my velocity at 6 seconds is 2.4. My velocity at 10 seconds is 9.6. That's going to break down to 7.2 over 4.0. I put that in my calculator. I have 1. Make it big. I like that one. Well, point. Can I get a point? 8. Don't pop up on me. There you go. 1.8. And this is acceleration. I gotta change it up again. As meters uh, per second squared. That square point, when we're talking about acceleration meters per second squared, what we're really talking about is changing every second. So from every second, it's increasing its speed or its velocity 1.8 meters for every second. So that's what it's talking about. So every second that passes is getting faster and faster and faster. That's why you see the graph rise. It's not staying the same. It's changing. It's changing, increasingly changing. It's getting faster and faster. So every second that passes is going almost 2 meters faster. That's like 5 to 6 feet. It's getting 5 to 6 feet, increasing the speed. Okay. All right. So we got that. Next slide. I can erase some of it. I'll move on down. All right. Don't want too messy. My screen. All right. Keep your eyes open. I consider the data in the science class. It's pretty simple. All right, so different masses were thrown at various amounts of force. The data reflects Newton's second law of motion. Force equals mass times acceleration. Based on the data collected, what conclusion can be stated about the object's acceleration? So these are various objects. Different masses were thrown. So this table represents different masses: mass 1, 2, 3, and 4. Okay, so I have force equals mass times acceleration. I want to find the acceleration. I must solve for A. So I got force equals mass times acceleration. Again, I have to solve for A. How to get acceleration by itself? Had to divide away mass. Anything divided by itself, we cancel it out, is equals to 1. So I have force over mass A. You can write it differently if you want to. Make you feel better to have the A in front. You can very well do that. So I'm using this formula and I'm plugging the values from this table. So I got force, mass. So the force is 25, mass is 5. So I can do this in my head. 25 divided by 5, that's 5. 50 divided by 10, that's 5. 75 divided by 15, that's 5. And that 20 divided by 100 divided by 20, that's 5 as well. Okay, so I got 5, 5, 5, 5, 5. So what does that tell me? What's that tell old Mr. Lewis? All right, that tells me that with this data, in all cases, the acceleration was the same for all objects. All right, acceleration was the same for all objects. Cool? Got that? Understand? Easy money. Next one. Make this graph a little bit bigger for some of y'all that was complaining in class today. All right, so it's 80, 60, 40, 20. So this is a position over time graph. We call this like a velocity. You can find your velocity graph. This is distance, centimeters over time, is seconds. So distance per time is the rate or the velocity or the speed of an object. All right, speed and velocity, they're nearly interchangeable. But when you talk about velocity, you're talking about a direction that goes along with that. So, okay, here we go. So I got this is over time, and I got different plots. So given the graph representing the position of the ball as they roll across the table, so balls rolling across the table, we want to quantify that, in the graph. So what is the ball's average velocity? So average, I mean, I need to take more than one measurement to get an average. I had to get like a measurement here, measurement here, measurement here, add them all together, divide by, the same number of instances I made those recordings, and I get my average. Okay. So we have to do some stuff, man. We got to do some stuff with this thing, right? So let's look at this problem a little bit deeper. So we set this line. And I asked my students earlier, like, what does a slope mean? So tell me, talk to the screen, like, what does a slope mean? All right, what is slope? All right, and slope mean how steep something is. Yeah, in earth science it does, right? But we're in physical science. All right, we want to understand the relationships between objects, right? So Listen, slope basically means the explanation of the variables at play at will. We want to explain the relationship between the x variable and the y variable, the independent axis and the dependent axis. That's what slope is. Slope would tell us, well, how does the speed of an object, or the distance of an object in this case, how does the distance of an object relates to its corresponding time? What do they have in common? That's what the slope of a line of this graph tells us. The relationship. We can see steepnesses, different steepnesses, but still you don't understand anything. But you put it in terms of relationships, we can understand that, well, on the y-axis and the x-axis, how are they like interrelated? Okay, that's what we're talking about. Very good, we got this. All right, now let's take some points. So pencil, pen. I have some science math class. You may put the y. I'm saying slope. So slope will equal my y2 minus y1 divided by x2 minus x1. Okay? Okay, get these lights on. All right. Oh, okay. So let's go ahead and find our x's. That's easy to do. My x2. I want to use these 2 points, I like the ones in the middle. It just looks so convenient to use those, right? So I have my x2 be the first one out, point 0.3 minus point 0.1. And then on dot, 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 hit that line, then go over dot, 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 dot. Oops, x2, excuse me. That's a 2 right there. I need to erase that. And then I have that 40 on that 2, 40 centimeters minus dot, 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 dot. So how you do that? 60. And so that's a little dot right there. So I get 20 divided by a tenth, 0.1. Difference between a point, that's a point right there. So we go a point 3 and a point, so it's 0.1. So when I divide right here, I had to move that decimal over to the right one time for dividing with decimals. I had to also do the same thing over here, the decimal over. So the decimal will be up here when I draw my line out. And that'll be 200. So the answer is 200. But what's the relationship? 200 centimeters over seconds squared. So every 1 second, this ball is increasing 200 centimeters. That's the rate if this graph or this slope go out into infinity. If it go all the way up here, can't even go off the screen, but it got to go off the screen. If I let this ball keep on rolling and 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 rolling, that's going to be a final outcome. You're going to reach to 200 centimeters for every second it's changing, going that fast. Okay? Yes, it is. Yes, it is. All right, so we'll go ahead and erase all that. I believe I don't need that stuff anymore. I'll mess up my document. All right, cool. I'll leave it alone. All right. Oh, man, I had a good little picture with this. All right, so, okay. I had a picture on my PowerPoint. I don't have a PowerPoint for you guys. But Carlos, he lifting weights. My homeboy Carlos, crap, erase that. Carlos is lifting weights on the bench press. He had a barbell. He got that. His arms, just a little bit over head right here. He lifted legs off the bench. Oh man, lifting. His back hurt. Okay, he got on some Jordans, trying to lift the front of the girl. He got a little hat on, trying to be like Mr. Lewis. Carlos lifting weights. Lifting. His arms kind of short. Okay, now Gravities, we all know, come straight down. Oops, bad line. Okay, straight down, what we call a perpendicular line. Perpendicular, what does that mean? We hear that word all the time. It means that something's an angle that makes 90 degrees. That's all. So the gravity goes straight down to make a 90. But Carlos want to be extra today. He want to be extra. He gonna lift weights on an inclined plane. So this is a bench with a bend in it. So Carlos, we go ahead, trying to be like old Mr. Lewis, got the little hat on, and so you think he buff and all that. Yeah, he got on them Yeezys and Tay. Okay, now Carlos lifted weights at the angle. Dark, put his arms a little longer. His arms grew this time, okay, class. So that force is coming down on that boy's shoulder. You're like, oh, I'm at an angle. It's more work. It takes more work. All right. So the greater the angle, let me go ahead and take this thing off. Oh, Carlos, long time ago. All right, so it's difficult lifting that much weight. 100 kilograms is like 200 pounds. You can't lift the same amount of weight at an angle because it messes with the forces of the gravity. So it's difficult with greater force of gravity at an angle. I have to kill this collar. I like get rid of him. Don't tell nobody. It'd be our secret. All right, fix my typo. Draw section 2. All right, at an angle. Okay, so difficulty with greater force at an angle is difficulty lifting. Can I fix that over there? So it's difficulty. So his body is not perpendicular to the point of gravity. It's not forming. Oh, well, it can't draw straight. Not forming those right angles. His angle is going to be gravity still pointing down. On an incline bench press is pointing down, but he breaking that plane up. So that weight still trying to push down, but he trying to lift it against that angle that he's at. So put him at a disadvantage. So that angle, let me erase that last one. His angle gonna change. It's the angle right here, part 45 degree, theta 45. Okay. That's tough, Carlos. It's difficult. All right, so we got two forces acting on the box sliding across the table. Which phrase could describe the motion of the box? So I got a force pushing hard to the right. This force 50 is kind of slowing it down. So friction probably from the box and the table. So if I had to sum that up, and write it out, if I type this stuff move, okay. I got to sum it up, write it out. I'll change it to red. I would like moving to the right, add its notes, and speeding up. That's what's happening. Move to the right and it's speeding up. Three force, keep on going. All right, two forces act on the sliding box on the table. The table has a mass of 20 kilograms. What is the acceleration of the box? Still the same thing. I got to find force equals, or acceleration, excuse me. Acceleration equals force divided by mass. Notice I'm using the lowercase a for acceleration because capital A is already used for a term called ampere. Okay. So we got the force. So these two different forces. I got 100 going this way, got 50 negative taking it away. So that's a difference of 50. 100 minus 50 is 50. All right. That's divided by 20 kilograms. That's the mass. So how many times can 20 go into 50? All right. It'd be 2 going to 5. How many times? That'd be 2.5 times. We're talking about acceleration, and so it's meters per second squared. Because again, a Newton is kilogram times meter per second, And we had a kilogram at the bottom, the 20 kilograms right here. That's the Newton. So that's meters per second squared. Sorry if I'm not using all these units. All right. So my homegirl Stacy, she's moving the 9 kilogram box with a net force of 45. Calculate the acceleration of the box. Same formula. So it's A equals the force, which is going to be 45 newtons, divided by the mass, which is 9 kilograms, 9.0, and that equals 5 meters per second squared. That's it. Okay. To break this down, so the Newton again is kilogram times meter per second divided by kilogram. Okay. This is in the numerator. I have to multiply by the inverse of this, so that end up being 1 over kg to get rid of this fraction. That's going to cancel out. All right. Excuse me, that's squared. All right. Force times acceleration, mass acceleration. So that's going to be left with this unit right here. That'll be our final unit. For those that want to be, superstar, smart kids, know about the units, that's how we do that. All right. So let's help you out. Help you understand.